Welcome back. So let's continue. I actually spent the break wondering, like, is there an example of a non-sequential unstructured data? But I keep thinking about that. It's a good question. All right. So I use analogies with spreadsheets regularly because, in fact, so we learn to do it the right way with the relational database systems. A relational database system, but in fact, a lot of the functionality is kind of available in spreadsheet as well. If you go to the ribbon and there's a few buttons that do something equivalent. All right, now, what about data models? Because we are going to look next week into the relational model and define it mathematically, but without scaring you. Not everybody loves math, but that can be an acquired taste as well. So, a model is abstracted from reality. It's an abstraction, right? So simplification, you kind of exclude what you're not interested in and focus on the future that are of interest. In fact, model outside of databases is very general, right? You can consider like modeling like that. Some people also build model planes. Maps also have underlying models. In fact, there's even professors and courses at ETH specialized in these things, in geographic information systems. There are physics models. Maybe you recognize the Schrödinger equation, which is one of the most beautiful inventions in physics. We have economic models, and so on and so on, right? And in our case, we are going to also have data models. What you see here is that's called the schema. It's the structure of some database, and that's the sort of things you see in companies when you are about to create a new database and you want to design it. Then you draw a lot of diagrams like this. What it says is basically, these are the tables we are going to have, and these are the columns that they are going to have, and these are going to be the types for the data that is stored in the columns of the tables, right? And then you get diagrams that look a little bit like this. Specifically, this one, I think it's called the TPCH benchmark, which is quite popular in order to measure performance in database systems. All right, but this is pretty much what it looks like, and this is also called the schema, but we'll clarify all this terminology with time. So that's the summary of what we have. I told you about the shapes, right? The 5 shapes, you have to know that by heart, right? Tables, cubes, graphs, trees, and text or unstructured. This is kind of the bucket where everything else goes, the unstructured data. In this course, we are going to cover the tables and the cubes, trees and graphs. This is done in big data. I think in big data for engineers, we focus on trees. With computer science master students, we also do graphs. And text, as I said, it's information retrieval. Typically, when you're talking about text, you mean a search engine and or a ChatGPT or this kind of application, right? Like large language models. Okay. Now, information systems. So what kind of information systems do you have? Well, it's everywhere. And in fact, I don't think if there is any company in the world that doesn't use in one way or another a relational database management system. Everybody has one. I think maybe at least from a certain size. The big players, typically you might have heard of them today, but it's basically Oracle, Microsoft, IBM. You can maybe throw in also SAP and a few others, right? And then there's a few open source databases like PostgreSQL, MySQL, and so on and so on. But basically, when you book a flight, it's all probably in a relational database. When you have a social network, okay, here it's probably not in a relational database because this is a bit less structured. In fact, this is why big data actually started taking off, but it's still a database system, even though it's not a relational database system. The inventories in supermarkets, this is also put in a database system. Google Maps, that's all stored in a database. Online stores, the inventory of, I don't know, Digitech Galaxus, this is all also in a database system. Newspapers, in fact, all the scientific papers, this is also stored in databases, typically in document stores. Very big fan of XML, the publishers. You know, my studies, you registered for the lecture, all of that, I'm pretty sure there's a relational database system behind it, where the lecture is stored. The booking the rooms, everything is in a relational database system. In fact, if you don't know what database system to use, there's 80% of chances that you want a relational database system, because this is usually what people need the most. I still wanted to say a few words on big data to put things in context, and also to be clear what we are going to do and what we are not going to do. What we are going to cover in this course is going to fit on your laptop. You can all have a database system installed on your laptop via Docker, and it will just be small enough to fit. But of course, as opposed to this, there is the internet and what goes beyond a single computer. And the scale is absolutely gigantic, but it keeps increasing. If you look at the amount of data that we consume over the internet, it just keeps increasing and increasing and increasing. And in fact, I think that what we created, I don't remember the exact ratio, but it's something like what was created in the past 2 or 3 years is the same amount as what has been created since the beginning of humankind, all the way to 3 years ago, just to give you the pace at which things are actually accelerating. And of course, a lot of the data that we create, this is not all information, there's a lot of noise. And actually the tricky part is to filter out the noise, to focus on the actual information, right? So just this gives an idea of the scale, and it keeps evolving, right? You see every year new systems that people use, and then people stop using the old system, so it keeps evolving. All right. When you talk about large scales and big data, this is the past 20 years. This is basically what has changed. It has changed in 3 ways. And again, I'm telling you that in order to put the limits to what we are about to do. First, the volume of data has increased a lot. And if you want to measure the volume of data, the quantity of data, we count that in bytes, right, or in bits. So a byte is 8 bits, right? You know that this is zeros and ones. And I'm pretty sure a lot of you at least know the first 4, kilobyte, megabyte, gigabyte, terabyte, right? Because this is the scale of your laptop. Anything that goes beyond that, like petabyte, exabyte, and so on, you might never have heard of that. And we are also not going to see that in this lecture, because this is when you start going to clusters, right? So all the way to terabytes, this is the kind of scale that we'll have in this lecture with information systems. I recommend you learn these prefixes by heart. This is very useful. It's actually not just for databases, but pretty much everything. The last 2, Rona and Quetta, are actually less than a year old. They are very recent. I think they had a problem measuring, I think, the mass of Jupiter, the planet, that they run out of prefixes. So they needed to come out with 2 new ones, and this is why we have Rona and Quetta. All right. But again, so you need to learn them. It's very important. But the first 4 is basically the scale that we'll have for the course. And also, this is kind of general knowledge, just so you're aware. We computer scientists love powers of 2. In fact, we love powers of 2 more than we love powers of 10. Which is the reason why in the very early days of computers, when we talk about a kilobyte, we didn't actually mean 1,000 bytes, we meant 1,024 bytes. Why? Because it's 2 to the power of 10. And that's really a coincidence, but it turns out that 2 to the power of 10 is almost the same as 10 to the power of 3, 1,000. So this is why in the early days of computer science, there was a big mess where when we said kilobytes, megabytes, and so on, we actually meant these, the powers of 2. And at some point, we decided to clean that a bit up and actually come back with actual prefixes for the powers of 2, and this is why these were invented. So kibi, mebi, gibi, tebi, and so on. I don't think a lot of people use them, but at least it clarifies that this is not the same thing as the powers of 10. You don't need to learn them. It's just so you know that. And I think Robi and Quebi are candidates, but they haven't been standardized yet. All right. But this is just general knowledge in science, not just computer science, that if you see these prefixes, you will know what they mean. Now in this course, even though we'll focus on the actual database systems, we will also talk about the ecosystem around them, the actual context in which these systems are used. And in fact, all of these systems, they are often hidden in the background. In fact, whenever you connect to a website like Amazon or Digitech Galaxus or any online shop, for example, there is a database system in the background, but what you will see is just a page. And it turns out that there is a whole computer system behind that that connects from the actual data where it is stored all the way through the database system, through the actual codes that ultimately generates the pages like this. But behind this, there is actually a relational database system. So this is called the front end. Maybe a lot of you already knew that. It's the front end as opposed to the back end. Right? So the front end is this. The back end is what you don't see as the user of a website, right? And of course, in the front end, it's displayed in a fancy way to the end user. All right. So now, what happens with data science? Well, if you just go to social media and try to learn data science, it's very likely that you will see a lot of influencers talking about Python and pandas and all these kind of things, telling you, okay, you should use Python in order to query your data. Well, it works, of course, you can do this. But it has problems because it doesn't quite follow the evolution of databases in the last few decades. And I would like in this course to make sure that you understand these things. So you could try this. You could, let's say, download a few files, like let's say comma-separated values or Excel files, put them on the disk, and then you can try to open a Jupyter notebook and write some Python, and it will work. You can even ask ChatGPT to write the Python for you, right? And that is actually probably going to work, maybe with a few iterations. So this is kind of the easy way, of straightforward way that you would kind of deal with data. It might work if you're just working on a small project, you know, and sitting in front of your computer and just grab the data you need and that's it. But as you can imagine, if you want to build a Digitech Galaxus on top of that, that's probably not going to work. You need an actual architecture and a structure in the way you do this, right? And this is what we will learn in this lecture. So let me first talk about the problems. Imagine that, so that you do on your own for one project, but imagine now that a company does that. Let's say 100 people or 1,000 people, and they start handling their data like this, and they're like an online shop, or I don't know. So they are going to maybe store that on their hard drives, you know, on their laptops or on their servers and so on. And they are going to handle everything with Python scripts in order to deal with the data. But there's going to be a few issues that will happen if you try to do that. So let's say you have the payrolls, so HR stored on some drive with Python scripts and orders and products, the inventory and so on and so on. The first issue is that you might store the same data twice or 3 times at different locations. That's called redundancy. For example, the payroll might overlap with the orders. I'm just trying to think of a naive reason, like, for example, your employees might also buy from your online shop, right? So you might have addresses that are stored twice. So this is called redundancy. You're storing the same data multiple times. So that in itself, you might think, okay, maybe that's okay. The problem is what happens if you want to update the data, right? You want to change somebody's address and so on. If it's redundant, then you might end up being inconsistent, because maybe you will think of changing the data on one of the machines or one of the drives or the databases, but not somewhere else. And then you end up with contradictions. And I'm pretty sure you've already seen that, right? Imagine that you move somewhere else and there is the same company that has your old address and your new address, and they didn't propagate it, right? To whom did that already happen? Nobody? It happened to me. Oh, a few of you. Okay. So this is an example of inconsistency, that you don't have a centralized design or a consistent design. Another aspect is that if the data is on Alice's laptop and some other data is on Bob's laptop, how do you combine this data? If you want to analyze and join, we'll see it called join the data. How do you do this if it's not on the same laptop? And again, maybe you'll manage, you can ask ChatGPT to write a script to connect to the other laptop and so on, but it's hard. It's not something that is actually so easy to do, right? So you might also think, okay, let's connect a drive to the network and have, it's called the network attached drive. and access it in that way. But then you're going to have trouble as well, because it will work with 5 or 10 people, but 100 people, you're going to crash the drive. It's not going to be able to handle something like that. So it's really, really difficult to actually combine the systems in this way. So these are some of the issues that you will encounter if you really try to stick to something like just storing files and Python scripts. And in fact, this is the reason why already 50 years ago, with actually Edgar Code, this is where it all started, they invented a new kind of software that does all of this for you automatically, and you don't even need to deal with that. So there is a top 5 of the perks that you get if you actually use a relational database management system. By the way, relational database management system, I might repeat so often that actually people have an abbreviation for that. They don't say relational database management system, they say RDBMS. So if you ever see RDBMS somewhere, it means relational database management system. You might also see DBMS, which means database management system. It's even more general. It's basically, it doesn't have to be relational. So just so that you know that if you ever hear me say DBMS or RDBMS, this is what it means. If you interact with database people, they will very often use this kind of abbreviation. So if you know it, you know what they are talking about. So the first benefit that you will get from an RDBMS is called enforcement of integrity constraints. When you are a company, and you might even have regulators that say how you're supposed to be running your business, or you might even have a few constraints on the data that you want to have, a relational database management system can monitor for the constraints. It can enforce them. For example, you want for a specific number, let's say an account balance, to be positive. That is a kind of integrity constraint. Another kind of integrity constraint is that you might have, I don't know, in one of the databases, all of your customers, and then in some other database, all of the orders that they placed. Well, you have a constraint that says that whoever placed an order should be your customer, right? So there has to be a link between the orders and the customers. This is another kind of integrity constraint. It's called foreign key, primary key. We'll look into this in this course, right? So the nice thing is you get that out of the box from a relational database management system. It's part of it. If you do it with a script in Python or any other language, you have to do it yourself, right? Another aspect is the support for multiple users. So I told you, if you try to just have a shared drive, it will work for your family. It's not going to work for a business because this is not designed for this. But with an actual database management system, it can run on some machine and it accepts incoming connection. It can support hundreds or even the more evolved systems nowadays, thousands or even millions of people, or even hundreds of millions now if you consider even the social media. So these systems can support multiple users. That is something that a simple script reading a file on a drive is not going to be able to provide, support for multiple users. Another aspect is data loss. If you just store the files on your hard drive and your drive crashes, then you lose the data. Who has already lost data in this way? That you had data on your drive, you didn't have a backup, right? Some of you, it also happened to me. In fact, first, that's a reason to back up your data. So if you haven't backed up your data, you should back up your data, especially if you have semester projects or theses you're working on. Make sure you back up your data. In order to back up your data, you can also put it on the ETH servers, right? And ETH will back it up for you, right? It's a bit similar here. If you have a relational database management system, it's kind of, it has all the framework to deal with this, right? So for example, some of the systems can even be installed on multiple servers, and it will store it on multiple machines. Some might have integrated backup functionality in order to copy your data over like every week, every day, every month. So this is all handled by a system like this. Number 2, which is actually kind of linked to multiple users, is access control. This is also something you cannot get from a simple script reading from your drive. Access control means, again, you're a company, you might be regulated. you need to make sure that not anybody can read any data or even can write any data. An RDBMS supports users, so you can register all your employees as users and granting them the rights to read and to write to specific tables, right? This is all supported out of the box with a relational database management system. In fact, PostgreSQL does that as well. You can add users and you can grant the users the right to read and write to tables. This is also something you get out of an RDBMS. And the top one reason is it's simple, but it's saving money, saving development costs, both on performance and productivity, right? So let's talk first about productivity. Well, productivity just means that you don't have to do a lot of things yourself because this is already integrated in the system. What it means is that if you use scripts to read data, you might have 1,000 people re-implementing over and over and over and over again the same thing for themselves. Maybe they will paste it for Stack Overflow or take it from ChatGPT, but they will every time just re-implement the same things all over again. With an RDBMS, you have people that might be the top experts in the world for these things that will implement it just once, and then they will ship it as a product to millions of people, but everybody will use this implementation that was actually made by experts who didn't copy it from ChatGPT or Stack Overflow, right? So you get productivity and performance, and that directly actually saves on the costs, right? So these are the motivations for actually having an RDBMS, right? I have a question for you. Let's go back to the Clicker app. So today things seem to be working. So I'm quite happy. It means that they probably figured out where the bug came from. A couple of days ago, I would click on start and then nothing would actually happen. So how familiar are you with relational databases, what I kept talking about in the last few minutes, and SQL or SQL? So maybe you're like, what is this? Or you've heard of it, but that's pretty much it. Or maybe some of you have already programmed in SQL. Maybe some of you have already built websites with some relational database in the background. Or maybe we have power users here who know all the way to the 6 normal form. Actually, when I ask this question in the computer science masters, I actually get quite a few yeses for the last one. Oh, wow, we have one power user here. Change their minds. All right. So whatever you answered here, you're at the right place, right? The goal of that course is to show you relational database management systems, to learn SQL and so on. And then at the end of the course, you can use it for your own projects, for semester's projects, bachelor's thesis, master's thesis. If you have data that fits in tables, then maybe you can actually use a system like this and the SQL language. All right, perfect. So I just now have a good distribution. So we have half of you have just heard of it, and one quarter of you have never heard of it, and some of you have some experience. Even for those of you who already used SQL, in this course, you will find all the theory around it, right? Like database design theory and so on. So that can improve your proficiency in doing that. So now I'm switching back again, hoping that I did my homework well by preparing why I'm landing back. We'll see. Nope. Okay, I just go ahead and directly go there. That's okay. It's going to be faster than just loading it again. All right. So now, okay, so I told you it doesn't work with larger scales if you just use Python scripts to read the CSV files. So what do we do about it then? We have an application, it needs to access data. Well, typically, yes, go ahead. Maybe the microphone we can use so that everybody hears you.
Just want to ask, why is everybody using it? I obviously don't like that beneficial.
So there might be several reasons. One reason is that Python is actually, there are several generations of programming languages, right? A few decades ago, there was COBOL, Fortran, C, C++, Java, and so on. And the more time elapses, the more languages are designed in a better way and in a way that users can understand better. Another aspect is that now the kind of hardware and power we have for the machines gives us more flexibility in the design of the languages. For example, in Python, it has levels of abstraction that hide a few things. For example, if you use C or Java, you have to deal with, do I use a byte, short, int, long? Maybe you heard of these types, right? How do I represent integers? Well, in Python, you just have int, and that's it. So it's already kind of a level of abstraction higher in terms of functionality. The same goes for decimal numbers or floating point numbers. In many languages, you have double, float, and in big data for engineers, we'll see we even have the decimals with infinite precision. In Python, you just have float, you have a unique type, right? And it takes care of it. Also, a lot of the syntax in Python is very convenient. You have all kinds of convenient shortcuts in order to iterate on an array and so on and so on. So it's very convenient. And in fact, it's a great language. I mean, I really like Python. It has a lot of libraries. It has a lot of a very, very long list of libraries. It's very simple to install, right? With PyPy, you can very easily install dependencies. You can do data visualization and so on and so on and so on, right? So the fact that it has a very large ecosystem of libraries probably also contributes to this. But one of the important messages that I try to bring to my students, and in particular the computer science students, there is no such thing as a system or a piece of software or a language that is good at everything. That doesn't exist, right? So you have plenty of different software, plenty of different programming languages, and every language has its strengths and weaknesses. And in the case of data querying, to query data, Python is an imperative language, and I also have slides on that a bit later. Python is an imperative language in the sense that you have to tell the computer what to do. One of the lessons that we learned from 50 years in databases is that when you want to query data, you have a special category of languages that we call query languages that are just focused on querying data. They only do that, but they do it really, really, really well in the design. And so the message here is that Python is a generic programming language. When you want to specifically query data, then a tailor-made query language is actually a better approach, right? If you want to scale. And this is why we learn SQL in this lecture. So I think that this is probably the reason why Python is so popular. And then there is, of course, the word of mouth, right? That when something actually works out of the box, then it propagates and everybody wants to use it, right? So again, Python might also be great for a small project, right? You have a bit of data, you want to query it, you open a notebook and it works great. The statement I'm making here is it does not scale. That will not scale to a system for a company of 100 or 1,000 employees, right? That's the idea. So again, if I summarize what I'm saying, always keep in mind that when you have a project or do something in a company, you have different use cases, you have different constraints. There is no such thing as a language or as a system that is good at everything. So you every time have to decide for what is for my specific use case, the language I want to use. Right. Did I answer your question? Yeah, awesome. Okay. So then this is actually kind of following, continuing your question. So this is a good transition. How do we scale then if it doesn't work just using a language on top of the data? Well, there is a very popular approach that established itself over the past few decades, probably even 40 years now. It's that we kind of split this into three parts, the application part. We have a part at the bottom that is kind of the persistency layer that deals with the data itself, that is directly connected to the data here. Typically, this is where SQL is going to be, the query language. Then we have the business logic. It's a fancy name, right? But this is what it's called. That is right there. If you know languages, maybe here you can think of Java, PHP, like this is typically C++, even Python. Some people might use Python at that stage, but still with SQL there. Even JavaScript became popular on the server side recently. And then you have the user interface, which is pretty much HTML and the web page when you're visiting the website. And so this three-layer architecture is extremely popular. And many, many, many websites that you have out there are actually building on an architecture like this with these three layers. So what happens is that if we start with the example that we had earlier with a hypothetical company that would just use a single language to directly access drives, then let's split it in three here. The first thing that's going to be done is some sort of integration, right? Instead of storing the data separately, everybody on their own disk, we integrate that into a single database, right? And the way it's done, of course, I'm not saying it's easy to do, right? But there are technologies that can do that can distribute the data physically over multiple drives, but it exposes it as a single database, right? You have a single entry point for that. So again, I repeat what I said earlier. A database, that's the data itself. The clay tablet that I showed you that is 1,000 years old, this is a database, right? The database is the data. Database is not a computer, it's the data itself. So we have the database here. And you can imagine a group of engineers that are very talented that deal with the details of how this is actually physically stored on disk, right? But we have this database. And in fact, so it's going to be stored on disks. And in order to handle that database, this is the actual software, the computers that kick in, the database management system, DBMS, right? And so the database management system is also fully integrated, typically across the entire company. You have a few servers running the database management system, could be Oracle, IBM, Microsoft, PostgreSQL, whatever, but it's fully integrated. There is a single access point. And this database management system deals with the databases. What does it mean? As a user, you don't even need to worry ever again about these disks. You don't care about them anymore. Why? Because that was outsourced to the database management system. Now, as a user, you only connect to this database management system and let it deal with the drives and storing the data and doing the backups and controlling access and so on. So this is already a huge improvement in terms of robustness for an enterprise-ready architecture. Of course, just for the sake of completeness, here, there is a single database management system, ideally. Now I have to tell you about the real world, and maybe some of you actually work in companies and know that. There are many companies that don't have just one DBMS, but might have 2, 10, 100 DBMSs, right? As a concrete example, maybe in the same company, you might have a PostgreSQL server and then a MongoDB server and so on and so on and so on, right? This is the real world, right? This is how it is. Here, I'm taking kind of this simplified idea, let's say an SME, a KMU, a small company that has purchased some Oracle license or that took PostgreSQL, which is free, and runs it on the server. And then everybody can just connect to PostgreSQL and directly interact with it, right? Does it make sense? Okay. So this is the first step towards a more robust architecture for a company. And now, so here I'm throwing terminology at you. So the database is the data, the database management system, DBMS, is the software. The two together is called the database system. So the database system has the data plus the management system, right? So it's very important, the terminology. Again, the database is the data, the DBMS, that's a piece of software that manages the data. The database system, this is everything taken together, right? Database system. Okay. And now I'm going back to data independence. I told you I'm going to say this probably 100 times in this course. So data independence is this what was coined in the 1970s. It's this separation between the physical and the logical layer. In a way, this is already data independence, what we did here, right? Because we disconnect the users from the disks. They don't even touch the disk directly anymore, and they go through the database systems through the database management systems to access the data. But conceptually, what is data independence? Data independence is this general idea that you disconnect between two layers, a physical layer and a logical layer. The physical layer takes care of the details. The logical layer is what the users see. And the idea is that in the case of an RDBMS, a relational database management systems, your users just see tables and relationships and that's it. That's all they see. And the physical layer is dealing with the files and the EDCs and so on, but the users don't even see that or even don't care about it. It's like automagical. Everything just works. That's pretty much it. So this is the idea of data independence, right? 1970. It's already now 53 years old. So you see how this is really getting established. And this is really, again, this is undisputed. Like this architecture, the vast majority of companies today work like that with their database management systems. This is how it works, right? Okay. So now again, conceptually, one of the other aspects of data independence in terms of benefits is that we have the logical layer, the table. We have the physical layer. In that case, that's the storage. There's also a compute, but let's focus storage, files and directories. The beauty of data independence is I can change the physical layer without touching the logical layer. And that is really beautiful and productive. It means that technically, so here it's a database, let's say in the 70s, or even still today, a relational database system, stores it on some server as files and directories hidden from the user. What if we consider this as the physical layer instead? Conceptually, the logical layer is still the same. You still have tables, you still have rows, you still have columns, but now instead of a drive, a hard drive with files and directories, I'm using clay tablets. In fact, this is what people were doing 4,000 years ago. That's exactly what was happening. They were having a database. They had a database management system. It's just that it was humans, the scribes, that were basically taking care of this. And they were already storing, you know, I told you the inventory and the orders and so on. Well, 4,000 years ago, they were already storing that kind of data. It was already inventories and transactions and so on that was on clay tablets. So in a way, we've had them for thousands of years, these database systems. But you see, data independence, the concept of the tables stays the same. We just swap the physical layer. And the beauty of it is that you can also, instead of a single machine or files and directories, you can put like 10 or 100 machines in there, and it works too. That's an entire cluster. In fact, if you're Digitech or Amazon, this is what you have. You don't have a single machine. You have an actual entire cluster of machines in there. But you didn't change anything to the logical layer. You're still dealing with tables, right? So this is really, really for productivity, really, really fantastic. And for performance too, because again, storing relational tables on top of a cluster of 100 machines, you really, really need to have the training for that. These are really like top-class engineers who learn these things. But the end users, they don't need to care about these things. They just work with tables and rows and columns, and it just works, right? So this is really a very good separation of concerns. And this is something I also love to show, is that technically, you can also store, instead of computer or clay tablet, you can also store it on DNA. In fact, people did that. I'm thinking one of my colleagues who was at ETH Zurich actually before, now he's in the UK, they managed to store relational tables on DNA, on actual DNA, and to execute SQL queries also on DNA. And this is really nicely illustrating data independence because again, this is just yet another physical layer, but the interaction still goes through a table. So this is the motivation for why next week we will look into the relational model like this, right? So logically, I'm just keep repeating the same thing, but just with various angles, right? I have this physical layer with my drive with the files and directories. I have a conceptual layer, a logical layer with the tables. The physical layer changes very rarely. I mean, the way you structure things is part of the software that you purchase. The schemas of your tables, they still change, but maybe still a bit rarely, right? You're not going to redesign your database systems every day if you are an online shop, right? And then you have, so this is now the UI. these are the views on the data, the fancy pages that the customer see. That can change often, but you don't need to actually change the schemas or even the way you store on the disk, right? So just to put it in perspective. Do you want to go and have lunch, or do you want? So let's do a vote. Who would like to now go for lunch? Who would like me to continue in the last 5 minutes? Okay, there's a bit more. So I'll just use the next 5 minutes. Okay. All right, I just asking because I know that when lunch arrives, usually the brain concentration starts to diminish. So just want to make sure that I still have your full focus. All right, now I'm going to talk about the kind of people who work, like the positions in companies related to databases. So we have people, the backend engineers, the database administrators, they just configure the database systems in the background in a way that everything runs smoothly, right? They coordinate, they check that everything works. If something crashes, they just purchase new hardware, and so on, right? Then you have people, the database designers that are structuring, designing the schemas and so on of the tables, the columns, the types, and so on. Then you have power users. These are the people who not only know SQL, they also know Java, they also know Python, they also know PHP, and so on and so on. So they're able to actually write computer programs, the business logic that uses SQL. So in other words, I'm not saying you will no longer use Python or Java or these languages. I'm just saying that you will use them together with SQL and use SQL in order to access the layer of storage, right? Then we have people that might not be good at Python or Java and so on. They just are going to write SQL queries, right, on some interface and query and update, maybe the data analyst, maybe in a Jupyter notebook. Then there are parametric users. These people don't like to write lines of code, so they just have a form that they can write into. Like, do you know Microsoft Access? Back then, that was one of the ways to access a relational database in this way. So it's just a fancy user interface, and you don't even need to type any SQL in there, right? There's a lot of enterprise software like this. Even at ETH, we have plenty of software like this that works with masks and views, but it's actually on top of a database. Right? So in terms of architecture, again, I keep repeating the same thing with different angles. So that I told you, the database management system on top. Where do we store things? Could be a local hard drive, could be on the local hard drive on a server. So the first case that you, during this course, you're going to store it on your own laptop. Then you might have this on a server, or you might have a shared drive, but only the database system accesses it. Or you could have a fully distributed file system on thousands of machines, but here we are talking about big data already, right? If I throw a few more fancy words, internally, the DBMS, we call it a data manager that manages the files, and we have on top of that a data manipulation language. It's in order to insert data, update data, and so on. It's going to be SQL that does that. Then you have the same thing with metadata. What do I mean here? The metadata, if you want to change it, it's like adding a column, modifying the type of a column, renaming a column. This is metadata. Data, modifying data, it's changing the address of a customer. That's data, right? So this is why we distinguish with changing the actual structure, the schema, with data definition languages, versus changing the data itself, the content of the table with data manipulation language. Okay, I'm going to stop here. Just have a few more slides to go, and next week we'll dive right into the relational models, right? So thank you very much, everybody. I hope you enjoy your lunch. No exercises today. It's going to start next week, and I'll see you at 10 a.m. in the same room or on Zoom. Thank you very much, and have a nice weekend.